Hello everyone, I welcome you all to the 12th video of module 5, and here we're going to talk about the gradients of the cost function with respect to model parameters, then what exactly is this gradient descent and how do we implement this, and finally we'll be deriving the equations for the backward propagation for the student who are really interested to try this out in your own system. So with this being said, let's get started with this particular video. And now the time has come where we go ahead and code for the backward propagation equations. Now don't really get scared by looking at this kind of derivative equations because I'm going to help you derive them at the end of this video. But right now, because we are in that flow, because we have already coded this cost function which is looking very similar, you can see that the summation part and then dividing it by n is just similar, and only this part will be different when you talk about this derivative equations over here. You can see that both the starting part is same, only the inner part is different. So coding this gradient descent will not be that difficult, and I don't want to break this flow, and therefore I'll be explaining the derivative of how did you get this kind of equations, from where did you get this kind of equations at the later part of this video. For now, let's focus on how we can implement this gradient descent so that in the next iteration I will be able to decrease the value of this cost function based on that update of the W and B. So what's really going to happen? After running that gradient descent, this W and B value will not be 0, 0 anymore. It will have been updated, and because of this updation, your cost function will be different, and we hope that everything is fine and this cost should be less as compared to what we are seeing over here currently. So that's the goal that we are going to deal with, and let's get started with the coding process. Over here I'm going to have a little bit of changes where I like to have a description for any type of function that I'm coding. So I'll just copy this whole part very quickly, go down over here and update this part. If you like, you can also do this. It's always good to have this type of documentation. All right. So this X, Y, W, and B, let me also rearrange them very quickly. X, Y, W, B, and then we're also having a learning rate. What is this? This is the step size that you will be giving to this type of derivatives, the partial derivatives with respect to your model parameters, right? So learning rate is your alpha value, which is nothing but the step size, right? And what is it going to return? It's going to return the updated values of W and B. This is something that I want this particular function to do. So return what? W and B, but updated values for W and B. Initially, it's going to get this weight and bias value, but at the end of the function, I am going to return two things: the updated values of the W and B. All right, so how are we going to code this? I'll just get rid of the extra spaces in between. All right, so how do you get these things done? We know that over here, I'll be requiring two things: the partial derivative of the cost function with respect to the weight as well as the bias. So for this, I'll be writing, let's say dj, dw, and it's going to be the same kind of thing that we had seen over here for the cost function. Instead of having mean of a squared error, you are going to have mean of this particular thing. Over here, mean of this particular thing. And if you really see in both these equations, the only one difference you will see is that here x is getting multiplied with this whole equation, but over here that x is missing. So by keeping all of this in mind, let's go ahead and code for dj dw, then for dj db, and finally after this I'm going to update the values of w and b, and this is what I will be returning out of this particular function. So what is this dj dw? It's the mean of what? It's the mean of -2 times the x values. Okay, it will be the whole x array data multiplied by the y minus prediction, that is predict. And predict takes certain type of inputs, and remember, this inputs will always be in the same order as you have passed while they're defining that function. So I'll just go back to that part and paste it over here. Now to improve the readability of the code, I can divide this part into two steps. I know that y minus y prediction will always be present. So I'll just take that part out, okay, and have it over here. That is the error term. What is the error term? It is y minus predict of those inputs. And over here, I can multiply my minus 2 times x with that error term. So I'll say that it's minus 2 times x into the error term. Oops, I should have been writing it over here. And just like this, I am having np.mean of minus 2 times directly the error term without x now. So yes, everything is fine according to me. And now if you want to update the value of weight, how can you do it? You take the previous value of w, that is the value that we have sent as an input over here, and then you have minus of that alpha value, which is the learning rate, and you multiply this with the respective partial derivative of cost function with respect to your model parameter. So it is dj dw in this case, right? And the same thing will apply over here, b minus learning rate times db dw, dj db. And yes, once this w and b values will be calculated for us, this will be sent as an output. I guess there is a spelling error over here. It's a learning rate, learning. Great. So our update weights function is also ready, and I should not really call it as update weights. I just call it as update parameters. Update params. Okay, you can call it the way you want. Even update weights are fine, whatever suits you the best. But now because I'm also having bias over here, and that's what I would like to call it as update params or parameters. I'll run this code and I'll test this very quickly. Check the update params function. So I'm just going to copy this whole thing very quickly, paste it over here, and instead of x, it's going to be the training data, x train. This is your y train. W, B, and learning rate, everything is defined. I don't need to change that. It's W0, B0, learning rate is 0.01. So hopefully we'll be getting two values over here in the output. And the first value will be for the W. So this is W dummy. And the second value will be B dummy. Okay. So if I don't write this first of all and just run this as it is, let's see what happens. You got two values. One is this one and the other one is this one. So what does it indicate? This is going to return a tuple. Why tuple? Because both of them over here are in the format of a tuple. For example, if I show you what is this, like, 1, 2, and if I, let's say, give some h variable to it. Okay, if I'm having this 1, 2, and if I print, what is the type of this h? See what's going to happen. It's going to be a tuple, right? So if I just print h over here like this, let's see what happens now. It's a tuple indeed, right? So yeah, because of that reason, you got the output in the format of a tuple. And you can also save this like this, like, this is your W dummy, W dummy and B dummy. And then you can print it out individually if you like. But I guess I am satisfied with this output that I've got. And yes, guys, that's how the update parameters is working fine for me. And the next thing will be to go ahead and club this forward propagation and the backward propagation into the training loop. So now that we have done the coding part for the updation of the parameters, let's understand that how did we get those equations of the partial derivative of cost with respect to your weight as well as with respect to your bias. So for this, I'll be explaining you everything that you need to know to derive this particular thing. So for that, I'll have to start with the basics of derivatives. And I'm going to talk about over here that for a polynomial, how do you take the derivatives? All right. So these derivatives are nothing but the differentiation, right? So y is equal to, let's say we are having ax to the power of n. So over here, note that a and n both are constants. And then this x is your input variable, y is your output variable. Or you can also call it as independent variable, and this is your dependent variable. And if you have to take a derivative of this type of polynomial, the rule is very simple. You simply say that I want to find the derivative of this y with respect to your input variable or the independent variable. it is always take a derivative of a dependent variable with respect to your independent variable, which is essentially telling you all that if I'm going to change this x a little bit, very little bit, then what will be the effect on y? What will be the effect on y? Alright? And the rule is pretty much simple. You keep this ax as it is, you don't change that. But now you take that n in the power, you bring it down and multiply it with that a and x. So it is n times ax to the power of, and now decrease the power by 1. This is as simple as it becomes. How do we take the derivatives for this type of polynomials? So for example, if I am having, let's say, y is equal to 3x square, and if I want to find out its derivative, how can I do it? It will be simply dy dx is equal to 3 times 2 is 6, so it becomes 6x, and take away power by 1. So it's going to be 6x to the power of 1. So this is how you deal with the derivatives. After this, there is one more thing you need to understand over here, is the chain rule of the derivative. So I'll just mention it over here, that what is the chain rule of the derivative. So in the chain rule, you basically have multiple functions encoded within other functions, and then you start taking this kind of derivatives of the inside functions and ultimately get the final derivative of the functions. I'm not really going to go into the depth of everything of the chain rule. Rather, I'll be just explaining you this thing as in how do you use this kind of a trick to do this chain rule very quickly. So let's say now you are having this equation y is equal to, instead of having just ax to the power of n, you are having ax plus b to the power of n. And let's say it's also multiplied with some kind of a constant over here, k. So now over here, this k and n are the constant. This is some different function ax plus b that you can think of. And then together this becomes k times some times of a function of x to the power of n. Again, we are having the same form as you can see over here. But now instead of having just a simple x, you are having some function of x, or this is also a function of x actually, where that function of x is actually your x. So now let's look into that. If you are having this sort of equation, then how do you deal with this? So for this, I'll be actually going ahead and showing you the rule with respect to this k times f of x to the power of n. Because the formulas are pretty much same, so it will be very easy to understand what's happening. So it's dy dx, do the same process, okay? There is no difference. Bring n down, so it becomes n times k times f of x, and then decrease the power by 1. But after this, there is a whole lot of thing going on. That is, you multiply this whole output of the derivative with one thing, and that is the derivative of this inside function. Okay, don't worry, this, if f of x is the original function, then this f dash x is actually the derivative of that particular function. So over here, if I have to go ahead and differentiate this with the help of this rule, let me go ahead and show it to you how we can do that. So over here, if I have to take derivative of this, it's going to be simply bring n down with k, so it's going to be n times k, then ax plus b to the power of n minus 1, simply multiply this with the derivative of this part. And if you can see, this is again a function of x, which is going to look like ax plus b. And over here, clearly we are having ax to the power of 1. So what will be the derivative of this? It will be 1 times ax to the power of 1 minus 1. And 1 minus 1 is going to be 0. So anything to the power of 0 is actually 1. So it's going to become 1 times ax to the power of 0. And because x power of 0 is 1, it's actually your a. So whenever you are having a times some independent variable with the power of 1, the output of the derivative will always be the coefficient that is there with that x term, or whatever is the independent variable. And similarly over here, if you try to take a derivative of b, which is actually having x to the power of 0 over here. So if you take this 0 times this bx, 0 times anything is essentially 0, right? So the output of always a constant, like if you want to take a derivative of a constant, it's always 0. And therefore the output of the derivative of this is this. Okay. So let's say if this is your t, then this is your dt dx. That's what it is, and that is your a. And yeah, that's what I'm going to replace over here. Instead of this f dash x, that is the derivative of this, it's going to be a for this plus 0 for this, which is essentially your a. And that's about your how do you take the derivative of this type of equation. I'll give you one more example very quickly. Let's say I'm having y is equals to minus 2 times 3x plus 8 square. And now if I have to take a derivative of this will be simply dy dx of 2 times minus 2 is 4. Keep your function as it is, don't change it. Decrease the power by 1. Multiply this input derivative with this whole output. So what is the derivative of 3x plus 8? 3x derivative is 3. 8 derivative is 0. So it's essentially into 3. So the final output will be minus 4 into 3 is minus 12 times 3x plus 8. To the power of 1, I can simply leave it as it is. So this is my final answer. So yes guys, that's how derivatives work, and this is how the chain rule works. Now after this, what we are having is partial derivatives. If you understand these two things properly, then understanding partial derivatives won't be that difficult. But before that, I'm just going to save this particular part, and I'll just call it as 3M7 and create a new paint. Going to paint it black, and now comes this part, that is partial derivatives. So now what happens in the partial derivatives? These are the fun part. So let's say if you're having this equation y is equal to x square t square plus 3x t cube minus 3t plus 2x, something like, it's you are having a combination of more than one independent variable on your right hand side, and on the left hand side you are having one dependent variable. And now if you want to take a derivative of this y with respect to any one of the variable by treating another variable as a constant. So if I want to take, for example, derivative of y with respect to x by assuming that t is acting like a constant, therefore we call it as a partial derivative. Okay, this is the symbol which we call as dou bar, del. There are different names. Okay, it's just del y del x. It means I want to take partial derivative of y with respect to this variable. It automatically means that we need to assume all of this as constant terms. For example, I can write x square into t square as 3x square, where this 3 is nothing but your t square. Just giving you an example that this is a constant like this. Alright. So now if you take a derivative of this by assuming t to be your constant, the output of this will be 2 times x, then decrease the power of 2 by 1. So it is 2 times x to the power of 1 into t square. So 2x into t square is the output of the first thing. Now do the same thing over here. Do plus because there is a plus over here. What is the differentiation of 3x? Now again it's in the format of 3x power of 1. So its output will be 3. And therefore I'll be writing simply over here 3. And because t cube is just a constant, I'll multiply it with that without doing any kind of derivatives over here. And now because this is whole completely a constant term, I told you constant term's derivative is 0. So you can write maybe plus 0 if you like, but I don't need to write that. I can simply go ahead and take a differentiation of 2x. It's going to be plus 2. So that's the output for that partial derivative of y with respect to x. Just note that I have assumed everywhere t to be a constant. Over here, assumed t is not there and took a derivative of x square. After that, I just multiplied it with the t square. That's it. Similarly for all the terms. And just like in the previous slide, I had explained that anything into your independent variables to the power of 1, the derivative of this will just be equal to that anything. Why? Because 1 into anything will be anything, but then 1 to the power of something, your variable to the power of 1 minus 1 will be 0. So this term will become 1 in the derivative, and therefore it is anything. Okay, so that was just a quick revision for you. And here is the output for the partial derivative of y with respect to x. Now I can do the same exact thing for the partial derivative of y with respect to t. In this case, what is constant? Tell me guys, what is constant? It is x, right? So all the terms with respect to x are now acting like a constant. So over here, this x square is going to be a constant. So what is the derivative of t square? Instead of x, it is t now, which is a independent variable. So it is going to be 2t to the power of 1. So it's going to be 2t and then x square. Then plus, do the same thing over here. Bring 3 down, it's going to be 9. X will be as it is, and then it will be t square. And over here, it will be just minus 3. Again, for the same reason, anything into an independent variable power of 1, output is anything. Over here, this is completely a constant derivative is 0. So this is the final answer, guys. This is the answer of the partial derivative of y with respect to x. This is the partial derivative of y with respect to t. Now, if you are aware about this kind of ideology, then understanding the partial derivative of the cost function is not going to be difficult at all. Okay, so let's just go ahead and derive these equations of the partial derivative of cost with respect to weight and bias. So yes, I'll again save this part. I'll call this 4M7. All right, and create a new paint screen, paint it black, and comes the final equations for the derivatives. So partial derivatives for cost function, for MSE cost function. Okay, just ignore my bad handwriting. It's completely pathetic. I do get it, but yes, I'll surely improve very soon. So now I am having J instead of Y, I am having J as my output, and this is equal to average, or I can say mean, of the squared error, where in the squared error I am actually having Wx plus B. That's my prediction, right? That's the equation of the prediction. So y minus prediction square. So this is my J. Now what do I have to find? In the first place, I have to find what is the partial derivative of this cost with respect to your what? W. Or you can also do it for B. I'll be doing it for B in the second equation. So how does it work, guys? If you look at this equation, what does this mean? It is basically, let's say for example, we are having 2 rows of data. It means y minus y cap square for that one data, plus let's say this is your row 1, row 1. This is your y2 minus y cap 2 square, and then you divide this by 2. This is what it is. So it basically means that the derivative of this one term, if you find, you can simply add all the derivatives of the term together by using the same type of notations. So essentially the output we'll be getting over here will be something like this. You will be taking average of the derivative terms that you are going to get for all the rows in between 1 to n. So I hope this part is clear. Now comes the derivative of this part with respect to W. And remember, it's a partial derivative. So anything apart from W is going to act like a constant. Let's just keep that in mind. So over here, this X and B becomes your constant. W is the only one independent variable that you're going to think about. And again, this Y is also a constant. So if you go ahead and take a derivative of this, remember there is a power. So I'm going to bring down that power. So that's going to become 2. And after this 2, what do we have? We are having this bracket of that whole function as it is, y minus, then inside the small bracket we have wx plus b, and then I end this bracket up, and over here the power of 2 minus 1 will become simply 1. So this is the output that I'm going to get. But this is not it, right? I am going to apply the chain rule to take a derivative of that inside part, which is squared. So now what is the derivative of this whole thing that you see over here? Just think about it. Okay. So the derivative of y is what? It's a constant. What is the derivative of constant? It's 0. Okay. I can write 0 over here, but I'm not going to write that. And after that, you are having minus wx. Now x is your constant. W is your independent variable with a power of 1. Just like if I'm telling you what is the derivative of 2x, you will tell me 2. Like this, if instead of x, I write w, instead of 2, I write x. And then if I ask you to take the derivative of this, the output will be x. And therefore over here, the output of the derivative, or I should say partial derivative with respect to your w, is simply going to become negative x. And then negative b's derivative will be 0 because again this is a constant. So this is what I'm having over here. I can simply close the bracket and then I can just simplify this equation like this. It's 1 divided by n, summation of all the rows from 1 to n, and it's going to become simply minus 2 times x, and obviously it's with respect to the I, so for every rows in your x. So everywhere over here I'll just write I, over here also there will be I, and over here also there will be an I. Okay, over here also there will be an I. So minus 2 times x I times y minus y prediction, and again add I over here. Just because I'm running out of the space, I am just saying that this wx plus b is actually my y prediction. So this is the equation that we have seen in our coding. We are having minus 2 times x times the error term, right? Now do the exact same stuff. Just take it as a challenge. Pause the video over here and try to find out what is the partial derivative of this cost with respect to your b. The process is just the same, okay? So you can pause this video over here and try to see how do you get it. And then come back and check if your answer is matching with mine, all right? Or else you already have the answers because we have already coded and we had seen that this x will just go, everything else will be same. So yeah, you can just be fine with that. But yes, I'm going to code it. I'm going to show it how we can derive that as well. So 1 by n, and that summation of all the rows from 1 to n is just going to be staying the same because the same ideology for this equation and this equation, the same ideology has been implemented. Now I'm going to have again 2 bottom. I have taken this 2 in the bottom. I am multiplying it with my yi minus the same thing wxi plus b. I'm going to close these brackets, multiply it with the derivative of this inside part. So the derivative of y, again y is a constant over here, that will be 0. And then minus wx. Now because the independent variable is this b, so anything apart from b is going to be a constant. So this is also a constant now. So what is the derivative of this? It's going to be 0. And then you are left with this minus b. If I ask you what is the derivative of minus 2x, you will say minus 2. If I say what is the derivative of minus x, you will say minus 1. Just like that, if I ask you what is the derivative of minus b, if that x has been replaced with b, you will say minus 1, right? So that's exactly what is happening over here. The partial derivative of this minus b will come out to be negative 1. And therefore my bracket is going to be simply closed over here. I'll say that I'm referring to this part, but yeah, essentially I'm referring to this part because both of them are same. So yeah, that's why I took that example. You don't need to take a derivative over here of this, okay? We are dealing with this part. We need to take a derivative of this inside function. So I hope this is clear. And the final output, if you see, it's going to be this I is equal to 1 to n. And now it's going to be minus 1 into 2 is minus 2. And then the error term y minus y cap, and that's it with respect to your I. So that's how you derive these equations. And now you don't need this I if you are dealing with an array. You are just doing this array multiplications over here, or if you like, you can call it as matrix multiplications, and it's going to work like a charm for you guys, right? We have already done the coding process. This was the mathematical part. I hope everything is making sense now. So that's the end of this particular video over here. And I hope that you are now feeling confident in order to create this kind of a code for gradient descent implementation, and also create the kind of gradients by understanding any kind of derivatives, right? If you are able to do this, you will be able to have a loss function or a cost function with respect to your model. Now in the next video, let's go ahead and train the linear regression model that we'll be creating, and then look into how the outputs are going to look like.